Hi Rockridge, this is Mrs. Berger, and today we're kicking off Unit 4 with our day 1 of notes. We're going to discuss categorical data and probability. Hopefully by now you've had a chance to take a look at your homework, which was to read chapters 1.1, 1.2, 4.1, 4.2, and 4.3 and define these vocabulary words that we have here. That was your homework after your Unit 3 test. If you've got time to do that before watching this video, I highly recommend that. It'll make the notes go much faster. If not, though, follow along and we'll get those notes for you. You may have to pause and take those notes for yourself. Okay? So let's start first by looking at the 1.1 material and 1.2 material, which should be fairly familiar to you. So the first thing we discuss on our notes today is the difference between a frequency table and a relative frequency table. And so if you will, follow me along on an example. So remember way back a few lessons ago when we took the ages of everybody in your classroom. I'll just put some example data here. This isn't a real classroom, but perhaps we had a classroom that had some people that were 198 months old, some people that were 200 months old, 204 months old, and 207 months old. And the frequency of those people, of how many people were those ages. Let's say maybe it was a small class, it was a teeny tiny class, it was only 10 kids, and so we have 3 that were this age, 2 that were that age, 4, and 1. And so this was the age, and this is the number of times that it happened, right? The counts. Age and frequency. So, to answer our first question, the frequency table, that shows the counts, or the number of individuals. And do you remember what relative frequency was? Hopefully everybody's muttering to themselves, yeah, relative frequency was just the percentages, right? Relative frequency, if you were to add a column here for relative frequency, you could just say what percentage of people were 198 months old. And how might you do that? How would you find the percentage? Well, obviously first you'd need to know how many total people are in this class. If you added up all the people in this class, how many people do you get? Hopefully you see that there are 10 people in this tiny little class. And so the relative frequency of people that are 198 months old is 3 out of 10, or 30%. Same thing for the 200s, 20%. The people that are 204 months old, there are a lot of them, it's 40%. And only 1 out of 10, or 10%, is your 207-month-olds. And so relative frequency is a little bit different, right? Relative frequency, that shows the proportion or percent of individuals. Having a certain value. All of these are having a certain value. Alright, so you guys all know this. This is repeat from our discussion about quantitative data. We could actually use this for qualitative data, so we'll see that in your first lab. You're going to use it for qualitative data. Let's stick with quantitative just because it's so familiar to us. And let's talk about the difference between a bar chart and a pie chart. You guys have been looking at this, oh gosh, since elementary school, right? So you guys know what bar charts and pie charts are. I do want to remind you that a bar chart is not the same as a histogram. Bar chart has spaces between the bars on purpose. Okay, so bar chart, you may have your 198. Let's see, how many people did we have? 198, 3. So 1, 2, 3. So that's how many people are 198 months old. And you have 200 months old here, and that's only 2 people. And you have 204 months old. That was 4 people. That goes up there, 204 months old. And then your 207, you've only got 1. And we have spaces in there, and it means something, or it's supposed to have spaces in between, unlike a histogram. And then always remember, you guys have probably noticed that you keep losing points on your labs for not doing this. Make sure that you draw, label, and scale your axes, right? You've been losing points on your labs if you haven't been doing that. So here you would label this age in months. You've already scaled it, right? And actually I should probably put some more space. I should put a little more space between here because this doesn't look properly scaled, does it? I should have spaced these out appropriately, but make sure that you scale your axes. I definitely scaled my y-axis correctly. I just needed to label it. So I'm going to label that frequency. So this is the frequency that the 198-month-olds have, it's a frequency of 3. And then maybe I'll label this chart age in months. I'll throw that as the title of my chart. Make sure that you draw, label, and scale your axes. You will lose points if you don't. Okay. Bar chart, we already know what that is. Pie chart, instead of using my frequency table for a pie chart, the frequency table was super useful for the bar chart, but the relative frequency table is more useful for the pie chart, right? Pie charts use portions, and so the fact that 30%, and this is not going to be the scale, but 30% of my class is 198 months old, and then 20% were 200 months old, and 40% were 204 months old, and then of course the 10% you might have to call out here, 10% were 207 months old. I mean, it should always equal the whole, right? And we would label this chart the same as the other one, right? Ages and months. And we would make sure that we labeled all the different sections, okay? Especially if you've got callouts. Alright, that is a review from a long time ago. You guys should be very, very comfortable with these. Please make sure that you do those 3 steps when you're doing your axes. So let's jump forward to our section on probability. So section 4.1 in the book. Probability and law of large numbers were the first couple of definitions we needed to take a look at. The first thing I need you to pull out of the text about probability is that it is always a value between 0 and 1. Right? You're never going to have a probability greater than 1 or less than 0. And so like we saw with the relative frequency table, we saw values of 0.3 or 30%, right? All those values are going to be a portion of 1. And the book definition calls out probability as something that describes the proportion of times the outcome would occur in a very large number of repetitions. The easiest way to talk about this is flipping a coin, right? It's the most basic thing to talk about. If you flip a coin, what are your chances of getting a head and what are your chances of getting a tail? 50% to get a head, 50% to get a tail, or 0.5 probability to get a head, 0.5 probability to get a tail. Now, when we start talking about law of large numbers, that flipping the coin is probably the quickest way to understand what the law of large numbers is. If you were to flip that coin 10 times, is it completely out of the realm of possibility that you get heads 8 of those 10 times? Has that ever happened to you? Probably. You flip a coin 10 times, maybe you get 8 heads and 2 tails, right? That's certainly not 50% heads, 50% tails, but it could definitely happen, and we've seen it happen, I'm sure. The law of large numbers says that may happen in a small number of times that you flip the coin, but if you were to flip that coin a bazillion times, and I know that's not a number, a million times, a billion times, if you were to do that chance process, if you were to repeat it many, many, many times, the probability or the actual outcomes of getting those outcomes, the proportion of times you actually get those outcomes will be closer and closer to that expected 50%. okay? The more you move away from only flipping it 10 times, the higher you go from those 10 times up to 1,000,000 times, the closer your numbers are going to be to a 50-50. Maybe they still won't be 50-50 exactly when you get to 1,000,000, but they will be much closer than the 80-20 that we saw down at the low end, okay? So I'm going to put the definition of the law of large numbers here. You should definitely take notes about your understanding of the law of large numbers, meaning that you'll get those expected probabilities or those expected outcomes when you run the simulation or when you run the chance process many, many times. Okay. So the law of large numbers says if a chance process, and this could be flipping a coin, rolling a die, picking a card, shooting a basketball, if a chance process is repeated many, many times, the proportion of times a specific outcome occurs approaches its probability. So those are the book words to get us to our coin flipping example of only flipping the coin 10 times versus flipping the coin 1,000,000,000 times. Okay, the more you flip it, the closer it'll be to those specific outcomes, to those probabilities. Okay, to those 50-50 probabilities. Let's take a look at the example number 1 on your example sheet that you should have gotten. So our example number 1 on our example sheet says a college basketball player makes about 75% of her free throws. After making 5 free throws in a row, a sports commentator says she's due for a miss. Is the commentator correct to say this? And you must explain yourself why or why not. Now, a couple things. If this was a coin flipping discussion, it might be a little bit easier to picture. If you flip a coin 5 times and you have gotten 4 heads and 1 tail, you might think, oh, I'm due for another tail, right? I've already gotten 4 heads and 1 tail. But in actuality, your reason might kick in and say, wait a second, what I flipped before has nothing to do with what I'm about to flip, right? My chances of flipping a head or tail are exactly the same. We want you to read this problem the same way, okay? We want you to read this problem the same way. This college basketball player makes 75% of her free throws, okay? She makes 75% of her free throws. She's like a machine or a robot, okay? She makes 75% of them. 75% of the time she makes them, 75% of the time she doesn't. So just because she's made 5 of them in a row, that actually doesn't change her chances at her 6th step to the line. Her 6th step to the line, her free throw shot, has the same exact chance, 75%, of making it or missing it, okay? So we want to say that the commentator's claim is based on the law of averages, which is not correct. Okay? They shouldn't be making declarations on the law of averages. Her 6th attempt has a 75% chance of making it, just like all the other ones. Okay? And again, if we had phrased this as a coin flipping question, it might be a little bit easier to realize that the 6th attempt is still going to be a 50-50 shot. The fact that we've got a person in here that might be affected by, her arm might be tired or the crowd might be, getting into it. It kind of sometimes muddies the waters, but when you read these problems on a quiz or a test, we want you to think, okay, she makes 75%. This is a fact. She makes 75% of her free throws every time she steps to the line, okay? Alright, so let's flip over to lesson 4.2 notes. And let's get some baseline information here on some outcomes. So let's first think about how many different outcomes there are for rolling one single fair die. Hopefully everybody knows that a fair die has 6 sides. And so there are 6 different outcomes when you roll that die. You could roll a 1, you could roll a 2, You could roll a 3, you could roll a 4, you could roll a 5, or you could roll a 6, and so therefore there are 6 different outcomes. Now let's think about what the different outcomes are, how many different outcomes there are for rolling 2 fair dice. Think about that for a second. And hopefully you thought to yourself, well, I could roll a 1 on the first die and a 2 on the second one. A 1 on the first one. Oh, I apologize. Let's do this in order. A 1 on the first one and a 1 on the second one. A 1 on the first one and a 2 on the second one. 1 and 1, a 1 and a 2. You could roll a 1 and a 3. You could roll a 1 and a 4, a 1 and a 5, a 1 and a 6. You could roll a 2 and a 1, a 2 and a 2, a 2 and a 3, a 2 and a 4, and so on and so forth, right? Now, let's keep in mind, rolling a 1 and a 1, rolling a 1 and a 2, rolling a 1 and a 2 is not the same thing as rolling a 2 and a 1, okay? These are two independent die, and so getting a 1 and a 2 is a different event than getting a 2 or a 1. I'm sorry, a different outcome, A 1 and a 2 and a 2 and a 1 are considered different outcomes. Same thing with the 1 and a 3 and the eventual 3 and a 1. So if we're calling 1, 1, 1, 2, 1, 3, each of those different outcomes, can you now answer the question, how many different outcomes are there for rolling 2 fair dice? Hopefully at this point you've come to the conclusion there are 36 different outcomes. If you need to pause and make a list of all those different outcomes to prove to yourself that there are 36, please do so. I want to make sure that you feel comfortable with this declaration, that there are 36 different outcomes. Okay? Alright, so let's talk about what a probability model is. So since listing all of these different outcomes here and then putting the percentage of them happening would take up a lot of paper, let me pick a different type of activity and write you a probability model for it. Let's talk about flipping a coin twice. Okay, this will take up much less paper. Flipping a coin twice. So how many different ways could this have an outcome? You could flip it once, get ahead, another time, get ahead. You could flip it once, get ahead, another time, get a tail. Flip it once, get a tail, and then twice, get ahead. And then the last thing that could happen is you get a tail and then a tail. Those are the only different outcomes for the activity of flipping a coin twice. Okay, for the chance activity of flipping a coin twice. And since there are 4 different outcomes, and none of them have any particular weight to them, right? They can equally happen. One is not more likely to happen than the other. The probability of getting heads is 1 out of the 4. Heads tails is 1 out of 4. Tails heads is 1 out of 4. And tails tails is 1 out of 4. If you are to list all the different outcomes and the probabilities that each would happen, you have created a probability model. Okay? A probability model is a list of all the different outcomes and the probability of each of those happening. Okay, so this is a probability model. Now certainly, if we had continued with the purple up here for the rolling the 2 dice, we would have a probability model there as well. We would have 1, 1, and then we would say that could happen 1 out of 36 times, and we would go on for there. Okay, so that's a probability model. Now, one of the most important things to know for this section is the difference between outcome and event. So far we've been talking about outcomes. Okay? Outcomes. An individual result of a chance process. That's an outcome. And I want you to be specific in your examples. I want you to see what happens with these examples. So follow with me and write this down for your example of an outcome. One example is rolling a 1 and then a 6. Okay? So that's my example that I want you to use for outcome. And then for event, an event is a collection of outcomes. And the example I want you to use for that is rolling a sum of 7. Notice the difference. Notice the difference between an outcome and an event. There is a difference between rolling a 1 and then a 6 and rolling a sum of 7, right? The probability of getting the outcome rolling a 1 and then a 6, that probability is 1 in 36. That happens 1 in 36 times, rolling a 1 and then a 6, right? But rolling a sum of 7, that could be done many different ways, right? You could roll a 1 and a 6, you could roll a 6 and a 1, you could roll a 2 and a 5, you could roll a 5 and a 2, you could roll a 3 and a 4, you could roll a 4 and a 3. There are 1, 2, 3, 4, 5, 6 different ways that you could roll a sum of 7. To make the event of rolling a sum of 7, you have a 6 in 36 probability of doing that, okay? That's the difference between outcome and event. Please pause the video and study that for a moment if you have any need to have that sink in a little bit, because the difference between outcome and event is very important. Now, to discuss the probability, let's first of all talk about how we write these things, make sure that you know how to translate them. If we've got equally likely outcomes, such as up here with the flipping a head and then a head, 1 in 4, head and then a tail, 1 in 4. Those are equally likely outcomes. For equally likely outcomes, the formula for the probability is written like this. The probability of A is an event that happens, maybe rolling a sum of 7. We define the event of rolling a sum of 7 as event A. The probability of A happening is calculated by finding the number of outcomes in event A and dividing it by the total number of outcomes in the sample space. And we literally just did this. You didn't even have to think very hard about it on the last example, right? The probability of rolling a sum of 7, let's call this event A for now, right? The probability of rolling a sum of 7 turned out to be the 6 different outcomes that could make event A happen divided by the 36 outcomes in the sample space. So the probability of A is 1 in 6, 6 divided by 36, and whatever that is in decimals. Okay? I want you to make sure that you use this terminology, probability of A, going forward. Now let's discuss the difference between complement and complement rule. Now hopefully you've already taken a look at the text and you've got these definitions, so hopefully you're just making some side notes to what you've already written down. Complement is the probability an event will not happen. Okay. You may have seen this definition of complement elsewhere in your math classes, so hopefully you've got this definition of complement. Something's complement is sort of the opposite of the leftover, the probability an event will not happen. The complement rule, again, let's make sure we use proper terminology. The probability of A not happening, that's how you write that. The probability of A not happening, or A's complement, that's a superscript C. You should read this as the probability of A not happening, equals 1 minus the probability that it will happen. Okay? That's how you read that. The probability of the complement of A, or the probability of A not happening, equals 1 minus the probability of A happening. And you probably could have figured that out for yourself. We just want to make sure that you've got that rule ready for you in case some of the language gets a little confusing on your problems. The next thing I want to talk about is mutually exclusive. Mutually exclusive, and again, hopefully you've already got this written for you from your homework. Mutually exclusive events are two events that cannot happen at the same time. An NFL team can be in the NFC or the AFC, but it can't happen in both. Okay, so those are two mutually exclusive events. You're either an NFC team or an AFC team. In baseball, you're either in the American League or you're in the National League. You can't be in both. They are mutually exclusive. They have no outcomes in common. Okay. And later we'll see examples of you're either an athlete or you're not an athlete. Okay. All right, the addition rule for mutually exclusive events is quite simple. The probability of event A or event B happening is equal to the probability of A happening plus the probability of B happening. It's a pretty simple rule. The problem is people usually forget that they have to check to make sure that the events they're talking about and adding together are mutually exclusive. You can't use this addition rule for events that could possibly happen together at the same time. Okay? We have a different rule for that. So make sure that when you add the probability of A plus B, you're looking at two different events that can't happen at the same time. Alright, typically we pause at this point and get a count of the folks in the classroom that are male and female and that are athletes and not athletes. I'm going to go ahead and fill this in for the video purposes with data that I collected elsewhere. Okay, so if you are running this in class, you could possibly take your own data and fill in what we call a two-way table. But I'm going to give you some data that I've collected elsewhere. So again, we talked about male or female, athlete or not. These are mutually, for purposes of this example, these are mutually exclusive things. For athlete, it's either yes or no. And I'm going to say male, either yes or no. Obviously, if you're no on male, you're female. And in the example that I wrote, I had 10 people that were both male and athletes, 3 people that were male and not athletes, 8 people that were female and athletes, or not male and athletes, and 5 people that were not male, they were female and not athletes. Now we always have total columns on either side. And again, this is called a two-way table. They're terribly useful, even if we don't ask you to make one. They're really, really helpful in a lot of these problems, so I encourage you to sketch them on your own just to get your head in the game on some of these problems. And we always do totals of our columns, so we have a yes column for male of 13, meaning we have 13 males in the room. We have a no column of male of 13, meaning we have 13 females in the room. We have yes column for athletes for 18, that's 18 athletes, 8 non-athletes in the room. And both of these, if you were to add this way or this way, they should add to the same thing, which is of course 26. 26 total people in the room. Okay? So that's a two-way table representing our males and non-males and athletes and non-athletes, two mutually exclusive statuses. Now, we're going to be asked to calculate two different things. And even though they sound very similar, they are very different things. The first thing we're asked to do is calculate the probability of randomly selecting a classmate who is male and an athlete. The second thing we'll be asked to do is to calculate the probability of randomly selecting a classmate who is male or an athlete. These are two different things and two different calculations. Now, what I mean by randomly selecting a classmate, I'm literally saying somebody walks in with a blindfold on, spins themselves around, and just randomly points to somebody in the room. Okay, this is a completely random process of grabbing somebody from that classroom, or throwing everybody's name in the hat and pulling it out of the hat randomly, or random number generator, etc. So randomly selecting, randomization is going on in this. Randomly selecting a classmate out of this particular room that is male and an athlete. Look at your two-way table. Can you identify how many people are male and athlete? Hopefully you see that this grouping right here, male and athlete, yes to male, are 10 people, and there are 26 people total in the room. So the probability of randomly selecting a classmate that is male and an athlete is 38%. And I would recommend you always put things in percentiles just so you can get a real sense of probability. Now, different from that is finding a classmate who is male or finding somebody who's an athlete. That's a different question. Male, how many males total do we have? Males total to 13. So there's a 13 out of 26 chance of getting a male. What about athletes? Yes to athletes is this number here. That's 18 out of 26. If these were mutually exclusive events, we would just add event A plus event B and say that's the probability of getting those two events. However, you could possibly be male and an athlete. The fact that you have some folks that could be both means that those two events of being male and athlete are not mutually exclusive of one another. And we're going to need to subtract out the people that are both so that we don't double count them. Right now, those people exist in both of these numbers, and we don't want to double count them. So we will subtract out the people who are both male and athlete, these 10 that are both male and athlete, the 10 out of 26 that are both male and athlete. That's so that we can avoid double counting them. So if you were to do that, you would have 21 out of 26 chance of finding somebody that's male or athlete. Much better chance, right? That makes sense. There's definitely more of those. That's a 0.81 or 81% chance of randomly selecting a male or an athlete. Let's look at this another way, a very familiar way, something we've seen since elementary school, a Venn diagram. I want you to label event A here as this circle 1 and event B as circle 2. So male is circle 1, athlete is circle 2. And hopefully you remember how Venn diagrams work. The overlap area is where your people that count in both circles fall, right? So the 10 people that are both male and athlete go there. Now I caution you for what goes into the little partial circles. You don't want to double count those 10 people that are both male and athletes. The people here are only males that are not athletes. That totals, for our little example, 3 people. And the people here in the athlete circle that are not in the overlap part, those are the people that are athletes but not male, otherwise known as the female athletes. So that's 8 people. We don't want to double count people. If you've already covered these 10 people here, you're not going to count them in either of the other circles. Now, hopefully you'll notice that we have not accounted for everybody. We've only accounted for 21 people, and we had 26 people in the class. Who are we missing? We've got the males who are not athletes, we've got the males who are athletes, and we've got the athletes who are not male. We're missing the people that are not male or athletes. The 5 people that are not male or athletes, those are represented on the outside of the box. Okay, now we've accounted for all 26 of our people. So that's a representation of our two-way table right into a Venn diagram. Now, looking at the Venn diagram helps us understand a little bit better our last 2 vocabulary words that you should have looked up before today's lesson. And those 2 vocabulary words are intersection and union. Now, an example of intersection is our being a male and an athlete. That's an intersection, which is super easy to understand looking at a Venn diagram. Intersection, male and athlete, it's where the circles intersect, right? Being male and an athlete is considered an intersection, and it's where they meet. The notation for that, the probability of being a male and an athlete. That's how I write that. It's an upside down U. Intersection is written like that. And we saw from above that to calculate that, it's 10 over 26. Okay. Now, being a male or an athlete is called a union. Being a male or an athlete is called a union. And to notate that, the probability of being male or an athlete. That's how we notate that. And what we saw earlier is the probability of finding probability of A plus the probability of B, and then subtracting out those duplicates, those times that they were both, right? So that calculation looks like this. You find the probability of the first thing happening, the first event, and the probability of the second one, and then you subtract out when they happen together, right? Subtract out when they happen together, when they happen at the same time. And just to fill out our notes a little bit, just to remind ourselves, for our particular example, this is how that played out. The males, 13 out of 26, plus the athletes, 18 out of 26, minus the male athletes, got us that calculation. Okay? Alright, those are all of the notes. I'm going to start on some examples and run through a couple of examples with you, and you'll have to do the rest on your own and check with your teacher, okay? So let's take a look at example 2 from your example page, the blood type question. So blood type, you should know, blood type comes in O, A, B, and AB, right? There's 4 different blood types. Now, this is not a two-way table, okay? This is not a two-way table. This is just a table showing you the frequencies. This is a relative frequency table, kind of set out on its side. It's a relative frequency table. This is not a two-way table, okay? So these are the relative times that I guess somebody sampled some human blood, and it's got a random sample from some Americans. Now, whoever did this sampling somehow lost the data on what percent had AB blood. They didn't lose who had O, who had A, who had B. They know those percentages. They just lost the percentage on AB. But can we back into that? Can we find the probability of a person with blood type AB if we know all the other ones? Hopefully you're thinking to yourself, of course I can. I know that all of the probabilities add to 1. And so I simply need to take 1 minus all the other probabilities. The type O probability, the A probability, and the B probability. And I believe that comes to 0.04. So there's a 4% chance of randomly selecting somebody with type AB blood. Okay? 4% chance of somebody with type AB blood. Now, what's the probability of a person who does not have type AB? First of all, let's practice our notations here. I would love for you to practice by writing what we're trying to find is the probability of AB's complement, right? This is saying what's the probability of somebody not having AB blood? And of course, hopefully you've already come to the conclusion that it's 96%. Most people can look at that and say, well, obviously, if it's 4% chance that you have AB, it's 1 minus the chance of having it. So 1 minus 0.04 means there's a 96% chance you're randomly selecting somebody who doesn't have type AB, okay? Alright, hopefully that went fairly well for everybody. If you need to, pause and replay that to make sure you feel solid on that before the quiz. Alright, question 3. Question 3's difficulty lies in the wording, and so let's get some practice being tossed an entire paragraph of information and having to get through it. Company is trying to market a new program for a graduate school exam and has this information. 20% of its market are undergraduates in business school. 15% are undergraduates in something else. I'm going to call this not business. Okay? Something else. 60% are college graduates who are employed. What's the probability that the randomly selected customer, is a college graduate who is not currently employed? Now, the trickiness, again, is in the wording of this, and so I want to make this a little bit clearer, hopefully make a little bit more sense to you, and explain that there's only 4 types of people in this problem. Okay, so if you didn't already read that into this paragraph, there's 4 types of people. There are the undergraduates who are in business, the undergraduates who are not in business, the college graduates who are employed, and the college graduates who are not employed. And that's it. Those are the only types of people we can have in this problem. And I know that didn't necessarily pop out from the page, but that's how we intend for you to read these types of problems. Okay? So the probability that you've got somebody, probability that you have a college grad not employed was the 1% you weren't given. It's the fourth type of person, right? They're a college grad. They're definitely not an undergrad. They're a college grad who's not employed. So, of course, much like our blood type example, if we find the sum of all the other happenings, we'll end up with the one that we're missing, right? So 1 minus the probability of undergraduates in business school, undergraduates not in business school, and graduates who are employed. That will net us the percentage of people who are college grad not employed. So 0.05 is the end of that, or 5%. Okay, not many. Not many of the people that they're looking at are college graduates that don't have a job. Find the probability that the customer is currently an undergraduate. Now again, we're not talking about college graduates that are employed. We're not talking about college graduates that are not employed. We're only talking about undergraduates in business school and undergraduates not in business school. So to find that, the probability of an undergrad, that's the probability of undergrad biz plus the probability of undergrad not biz. And you could have put your little C if you want to get fancy. Undergraduate not business, or other. And again, why are we allowed to add them together? Because they are mutually exclusive events. There's no overlap. There's no intersection. You're either in business or you're not in business. Not both, right? You can't be not business if you are business. Okay? So we go back up in our problem and we find out what these are. Undergraduate in business, that's 20%. Undergraduate not in business, or other, is 15%. So that's a total of 35% are undergraduates in this pile of people. And the last part of this question says, find the probability that the customer is not an undergraduate business student. Well, remember, finding the probability of undergrad complement, right, is 1 minus the probability of undergrad. We just found, undergraduate in business. Undergrad in business, sorry about that. Let me just add it here. Undergrad in business is complement. Undergrad in business is complement. And so we know that the probability of undergraduate in business is, undergrads in business is 20%. So 1 minus 0.2 gets us 80% of these folks, these customers, are not undergraduate business students, using our complement rule. Okay. Again, pause and go back. Definitely the wording of this problem is what needed to be broken down the most, and understanding all the different categories of what we're looking at. All right, last one I want to walk through with you before I set you loose on your homework is question number 4. This is a question about randomly selecting a deck of cards, random events. If you need to, if you can fast forward through this section if you know what a deck of cards has in it, but if you need to, let's talk about the fact that a deck of cards has 52 cards in it. Within those 52 cards, you have 4 suits. Your first suit is spade, and that's a black set of cards. Then you have clubs, that's another black set of cards. Then you have hearts, that's a red set of cards. And you have diamonds, that's also a red set of cards. So hearts and diamonds. And then within each of these are called suits, and then within each of these suits you have 13 different cards. So every single one of these has an ace, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, a 10. and then something called Jack, Queen, and King. So those 13 cards are repeated across all the different ones, all the different suits. And the Jack, Queen, King cards are often called face cards. We don't typically include ace in face cards. We typically just look at Jack, Queen, Kings as face cards. And again, all of this gets repeated 3 more times in all these different ones, okay? So, in these probability problems, a lot of times we fall back on this standard deck of cards. Obviously, a standard deck of cards does not have jokers in it, so these are the 52 cards we're talking about, all right? And again, make sure that you have that understanding so that quizzes and tests will go a little faster for you. But that has basically been summarized a little bit in this question here. So, you're randomly selecting or randomly dealt a card, and you're supposed to be finding the probability of various actions happening. And we're going to say event F is considered receiving a face card, and event H is considered receiving a heart. And we put a two-way table together for you to summarize how those play out in numbers. So there are 3 heart face cards and 10 heart non-face cards. If you need to flip back to your reference, please do so to make sure you agree with that. There are 9 non-heart face cards and 30 non-heart non-face cards. Okay? So hopefully everybody agrees with all of that. So let's look at the first question. And again, we're beginning to practice this notation and understanding what we're even being asked in the first place. So take a look at that. See if you understand what you're being asked. Hopefully you have thought to yourself, I'm asked, what is the probability of not being dealt a heart? Okay, that's what that means. P of H with a C complement. That's asking, what is the probability of not being dealt a heart? All right, let's look at our table. How many non-heart cards are there? 39, right? Probability of not being dealt a heart is 39 out of what? Out of 52. Hopefully everybody's shouting out of 52. Now that gets down to a 0.75 or 75%. Now, you know me, and every time everybody that does probability and statistics, we never let you just answer a question with a number, right? The most dreaded word in probability and statistics, interpret, right? How many times have you lost full credit because you didn't bother to interpret your number? We're going to keep at it. Interpret this. What does it mean? What does P of HC equal 0.75? What does that mean in the context of this problem? Hopefully everybody's shouting. That means there's a 75% chance that a randomly dealt card is not a heart. If you had trouble coming up with something that sounded like that on your own, please pause, study that, make sure that you understand that that is how you will need to interpret this value. Okay, I want to make sure that you walk away from this with a strong understanding of why. All right, let's hit part B. Again, we've got all kinds of fancy notation. Let's make sure we understand what we're being asked. Take a look at that. Think to yourself, what are you being asked? What are we asked for? The probability of what in words? Hopefully you wrote down and thought to yourself, I'm being asked, what's the probability of being dealt a face card, that's what F means, face card, and not a heart. Right? Don't forget this little C there. Not a heart. Okay? Alright, well how would we do that? How many cards in here are face cards that are not hearts? We've got that on our table, right? Face card, not a heart. That's a 9 out of 52 chance, right? 9 out of 52 chance of being dealt a face card that is not a heart. So I calculated that out to be 17.3% chance. And I wasn't asked to interpret this value, but you definitely could, right? Alright, last one I want to go through on the video. probability of this, so take a second to read that, flip back to your notations. I know you're just now learning them, so I'm not expecting you to know them right away. Flip back to your notes, see if you can figure out in English words what you're being asked to do. All right, hopefully you saw that you're being asked to do probability of a face card or not a heart. It's a different question, right? Probability of a face card or not a heart. And remember, we can add these two events together, but we have to subtract out the duplicates, right? We have to subtract out the duplicates. So let's see. Probability of a face card. We already know that. That's a 9 out of 50. Or no, I'm sorry. Probability of a face card, total face cards is 12. So 12 out of 52. Plus all the not a hearts. Not a hearts. That's the 39 out of 52. And then we subtract out the cards that are both face cards that are non-hearts. Face cards that are non-hearts. That's the 9 out of 52 we talked about in the last question. So that comes out to be, we all have a common denominator, right? So we just have to take care of the numerators. That comes out to be 42 out of 52. Or 0.808. Or an 81% chance of randomly being dealt a face card or a card that's not a heart. Alright? So again, learning the notation is one of the trickier parts, and then interpreting that into English. I want you to go ahead and attempt the rest of the problems on your independent practice and come to us with questions, okay? Thanks so much, and we'll talk to you next time.